Ooh, don't fall. Okay, so we are given some information, and our question asks us to approximate how high the water would be at time equals 2.8. And then the second part would be, well, is our estimate an over or underestimate? And we have to give reason. It's asking us to use tangent line approximation, and well, and which means that we're just going to use the tangent line at the closest value that we know to estimate what the value would be at t equals 2.8. So in this case, we know our closest value that we know for sure is closest to 2.8 is t equals 2. So the first things first is that you have to write down the tangent line formula, and you might be familiar with it because it looks a lot like this, because a tangent line is actually just a line. So here, this is point slope form, and you probably remember it as like another way of writing down like mx plus b. And this is actually pretty much what makes tangent line, the tangent line formula, because we pretty much just take this and move it over here to get something like y1 is the slope times the change in x plus y2. In this case, let's rewrite the variables so that way they better match our formula. So since we're looking for the height of the water, let's let's use L for liters, right? So LT, because that is our function. That's what we're calling it. LT is going to be our slope. So, or M. Well, what's going to replace M in this case? We know that since we're looking for the height, we're probably going to have to use change in height to replace M. And we know that change in height, well, that's like, we know height, the function for height is ht, and therefore the change in height would be h prime of t. And would you look at that, they give it to us. So we're going to put down, but first we're going to take it slow. So h prime of t at what point? Well, remember, we are taking everything from t equals 2, because that is pretty darn close to 2.8. So h of t at 2 times our change in x, or I guess in this case our change in t, because we're looking at time. And our change in t would quite literally be the difference between 2.8 and 2. Awesome. Now what's our last part going to be? Well, that's why you look back at your problem, because in the information it says that at t equals 2, the height is 7 feet. But, you know, just to make everything kind of like cohesive, I'm just going to write it down as h2. Now, I want you to look at this and remember that this h of 2 is not the same thing as h prime of 2. They're very two different things, and I think it's really easy to mix them up. But they don't represent the same thing. So keep that in mind. Because this is height and this is change in height. So now that we have that though, we can start plugging in our actual values and start solving for our estimate. Plug in. So our slope h prime of 2, and they give it to us here in our table, which is just 0.3. Our change in x, or our change in t, 2.8 minus 2, well, that's just 0.8 plus h of 2. And we know from the problem, the information offers us that at t equals 2, the height is 7 feet. So we're just going to plug in 7. Awesome. This looks like something we can solve. So from here, we can actually just simplify it. And I'm pretty sure that's just 7.24, but let me plug it in. Yeah, all right, cool. So that is our approximation, 7.24 feet. All right, now we have to answer the next part, which is this thing an overestimate or underestimate of the real of what it would actually be? Because by the end of the day, this is not our real answer, just an approximation. Well, luckily for us, the problem actually makes it really easy because it tells us that the function is actually concave up. That is something that is known. Even if you didn't know that though, you should be able to look at these points and like really roughly plot them out and be like, okay, you know, actually, hold on, you can't do that. I lied. But we do know from the problem that it explicitly states that h of t is concave up. And if you kind of look at it, like from there, like you can immediately tell whether or not it's going to be over or under approximation. So remember, we're using tangent, the tangent line formula or the tangent line approximations in order to figure out what the, you know, or estimate what the real thing would really be, the real value. So let's say, oh my days, that is a terrible line. Let's say, you know, this is not, let's just look away from this and focus on this little plot right here. Let's say we got a little line, a little u, or yeah, something like that. If we're estimating from here and we use point slope form, that's not perfectly at the vertex, by the way, so it should be a little bit angled, because obviously, you know, whenever there's a time change, it would actually, your line would be 0 because it would just be horizontal because there's no change in the graph. But if you're taking it from somewhere from like here, your, let me use a different color, your tangent line would probably look something a little more like this. It looks really, you know, it looks like it's running across the line, but it's pretty, like, you know, the tangent line is just taking from the slope, because tangent line is just the slope of the slope, literally. And if we zoom in a little closer, we can be like, all right, well, when my line is a u, and like let's say we're taking it from here, my tangent line is gonna look a little like this. And this u is concave up. Concave up. Because it's, you know, making a little positive U shape. The water is inside your bucket. In a concave down, which means your bucket is upside down, your water is flowing out. And let's say we take it from like here, you're gonna notice that our tangent line looks like this. So what's the difference between our tangent lines here? Well, you can see in the concave up one, our tangent line is below, it's underneath the real line. And in concave down, our tangent line is actually above. So what do you think this means? Well, we know now that since concave up functions, our tangent line is going to be always under, that means that our estimation using the tangent approximation is going to be an underestimation. And it's kind of like vice versa for the concave down. since it's always above, that means it's going to be an overestimation. So traveling back to what we were working on from before is our approximation of 7.24 feet an over or under approximation. Well, since the problem was so kind to actually say that it's concave up, we know that our approximation using a tangent line on a concave up function, our line is going to be below the actual function, as we can see here. So that means that our estimation is an underestimation. Or is it, oh my days, it's an underestimate. Because the graph is concave up. And that's it. I guess some things to note is that not all problems are going to be nice and tell you whether or not it's concave up or concave down. And that is when you have to remember that, you know, you can figure out whether it's concave up or concave down without telling you using a graph. If they make you look for, if you're able to look for h double prime of t, in this case, yeah, because they give us h prime of t, which gives us the slope. But we need the slope of the slope in order to figure out whether or not it's holding water or dumping water out. And I don't know if Aiden's already taught you this, but when h of t is negative, that means it's concave down. And when it's positive, it's going to be concave up. And you should already know how to solve for like derivatives and stuff. And it's like pretty much the same thing. You know, nothing crazy changes when you're looking for like a derivative of a derivative. You're still, you know, kicking out the x, adding or subtracting something from the exponent side and whatnot. And yeah, so that's just something to look out for in the future. But yeah, all right. Thank you for watching.